Hello everyone, Mr. Hasty here. I hope you're all doing well. I got a request to do a video on the math from sections 11.1 and 11.2. And so what we're going to do is go over some of the basic definitions of stoichiometry, get a general plan of attack for how to handle all these problems, and go through 3 examples of how to do it. So, first of all, let's define stoichiometry. Stoichiometry, which is a fun word to say, hard word to spell, even if I have it right in front of me, is the study of the quantitative relationships between products and reactants. So what does that mean? If we take a chemical equation that we've used before, which is that 2 magnesium combined with oxygen gas, O2, will yield 2 magnesium oxide. That's a balanced chemical equation. The materials on the left, the magnesium metal and the oxygen gas, are our reactants because they are reacting to form our product, which is magnesium oxide. Now, when we look at an equation, balanced chemical equation like this, one of the important things to note is that that is a ratio of how many atoms of magnesium have to combine with how many molecules of oxygen gas. So we need 2 atoms of magnesium for every 1 molecule of oxygen gas to form 2 formula units, in this case, or particles of magnesium oxide. So basically we need 2 magnesiums and 1 oxygen gas to make 2 magnesium oxides. We're going to talk about moles because this is talking about them on the atom level. But remember, saying a mole is like saying a dozen. We need 2 dozen magnesiums, 1 dozen oxygen gases, and we'll make 2 dozen magnesium oxides. Now, what we're going to talk about a lot is a mole ratio. And what that is the ratio of the moles required in a chemical reaction. So if we look at our equation again, the ratio of magnesium to oxygen gas is 2 to 1 because the coefficient of magnesium is 2 and the coefficient of oxygen is 1. The ratio of magnesium to magnesium oxide is 2 to 2, which you could reduce down to 1 to 1. And the ratio of oxygen gas to magnesium oxide is 1 to 2. So that is what a mole ratio is. We're going to move forward into kind of our master plan for how to tackle stoichiometric problems. All right, let's talk big picture here. What we're really looking at is we have some compound or element A at the beginning, one of our reactants, and at the end we're going to get some compound or element B. And all we're doing is taking a mathematical journey that starts at how much A do we have to how much B do we end up with. We do that all through conversions using the factor label method. That's the box method that we used last chapter to do our conversions. So, the longest problem that you could get in this type of problem would be as follows. I'm going to give you a number of grams of A. I'm going to tell you how many grams that is. And we need to convert that all the way to grams of B. So using the method we've shown, we can convert grams to moles. So we could convert grams of A to moles of A. Now we'll talk about how to remember how to do that here in a second. Then we're going to use the mole ratio we just found to go from moles of A to moles of B. Again, we'll talk about how to do that in a second. Then we're going to go from moles of B to grams of B, which is usually the furthest we'd want to go. And our final answer will come out in grams of B. So where do we get these ratios from? The ratio here, which is moles to grams, and the ratio here, which is grams to moles, those are molar masses, which we learned to do last chapter. To do a molar mass, you simply look up the pieces on the periodic table. So for instance, if we have H2O, we would add 2 H's in terms of their mass plus 1 O, and I get these numbers off the periodic table. Now, if you don't have your textbook, you can look up a periodic table online, and it'll be fine to work with for what we're doing. Now, that's how you get those ratios. We did that last chapter. This part right here, the moles of A to moles to B, we have to look at our balanced chemical equation. And if we go back and look at this one up here, 2 magnesium plus 1 oxygen gas yields 2 magnesium oxide. We have to get our ratio by looking at the coefficients. If we're going from oxygen gas to magnesium oxide, we would have 1 mole of O2 gives us 2 moles of magnesium oxide. And that's how we would get that particular ratio in that problem. That is the largest potential problem we'd have. So how does it get shorter? Well, basically, they can ask you to start earlier. Instead of starting you at grams, they could start you at moles. And then your path is shorter. You don't need as much. Or they could ask you to end at moles. And then you don't have to do as much. So we're going to go through from shortest to longest the types of problems you could see. The first one is called moles to moles, which means we're going to start with moles of one substance and go to moles of the other. So we are reacting magnesium metal with oxygen gas to form magnesium oxide. Well, the first thing you need is you have to have a balanced equation. We've already talked about this guy to work from. Without a balanced equation, your ratios will be wrong. So we're going to start with 8.50 moles of oxygen gas. We're going to start right here. We're starting in the mole. And where do we want to get to? We want to get to moles of magnesium oxide. So if this is moles of A, this is moles of B. So we just need to get from here to here. So we don't need this part. We just need our mole of A to mole of B ratio. And where do we get that? From our balanced equation. According to this equation, 1 mole of O2 will give us 2 moles of magnesium oxide. Now, how do we know that's all we have to do? We end up in the units we want. We want units of moles of magnesium oxide, and that's what we have. So we do that multiplication there, and respecting sig figs, we get 17.0 moles of magnesium oxide. Now I said respecting sig figs, but you might look at these one-digit numbers and go, doesn't that limit us to 1 sig fig? Well, those are not measured numbers. Those are ratios that are universally true from our equation. The only measured value is this 8.50 moles. So we are done because we have the unit we want. We're going to move on to a second set of problems. So for the next two problems, I'm going to use the same chemical equation just to make it a little bit quicker. what we're going to be doing is we're going to be combining methane gas, which is CH4, with oxygen gas to form carbon dioxide, good old CO2, and water. Let's balance that quick. It's always good to do some balancing practice. So I have one carbon on the left, I have one carbon on the right, good. I have 4 hydrogen on the left, but I only have 2 hydrogen on the right. I'm going to need to double my hydrogen here. I have 2 oxygen, but I have 2 oxygen on the left, but I have 2 oxygen with the carbon dioxide and 2 oxygen with the double water. So I need a total of 4 oxygen on the left, which is easy enough to do. We just make that a 2 right there. Double check, 1 carbon, 1 carbon, 4 hydrogen on the left, 4 hydrogen on the right, 4 oxygen, and we have 2 oxygen from the carbon dioxide and 2 oxygen from the water. We're good. So now we're going to do a mole to mass calculation. We're going to start with a certain number of moles of methane, and we're going to go to the mass of the water. So we're starting with 4.55 moles of methane, and I'm going to take a second to flip back and show you kind of on our chart how this works. We're starting with moles of something, and we're going to go all the way to grams because we want mass. So we're just going a little bit further on our chart. So 1 mole of methane, and we have to come up with a molar mass. So where do we get a molar mass from? Or sorry, we're doing a mole to mole ratio here, I apologize. So after we do the first one, we have to go mole to mole to convert to our new substance. So we have 1 mole of CH4, and that's going to correspond, we're going to water, so that's 2 moles of water right here. So we're going to have that ratio right there. If we start with 1 mole of CH4, we're going to end up with 2 moles of water. Cancel my units. So now I don't want moles of water, I want grams of water. So we have to do a molar mass. So how do we do a molar mass? You go on your periodic table and you add up 2 hydrogens, which are 1.008, and 1 oxygen, which is 15.999. When you do that, you get 18.015 grams of H2O. Moles cancel, and we know we're done because we're in the unit we want. We have mass, which is grams of water. So I do that calculation, and respecting that we only have 3 significant figures here, get 164 grams of water. All right, and now we're going to do the long one. We're going to start with a number of grams and go to another number of grams. So if we look back at our original chart here, we're going to start all the way at this star right here with grams of A and go all the way over here to grams of B. So we start with 50.0 grams of oxygen gas, which is O2. We have to go from grams to moles. So on the periodic table, we figure out that O2 would be 2 times 15.999, which is 31.998 grams of O2. That's what 1 mole of O2 is. Now we have to use, to go from O2 to CO2, carbon dioxide, we have to use the ratios in the problem. If we look there, we have 2 O2s, gives us 1 CO2. So 2 moles of O2 gives us 1 mole of CO2. And finally, we don't want moles of CO2, we want grams. So we have to do another molar mass calculation. We have to look up and add up 1 carbon with 2 oxygens. And when we do that, we get 44.9 0.009 grams. So we do the calculation. Remember, you multiply the numbers on top and divide the numbers on bottom. And respecting 3 sig figs, we get 34.4 grams of CO2. I hope this video helps to clarify some of the confusion that's been going on with this material. It is a bit of a process, but it's a process you really need to get down as you move forward in chemistry, because determining how much are we going to make when we make a chemical reaction or do a chemical reaction is very important for practical chemistry purposes. So I hope this helps out. We'll talk about it more later if it's still an issue. Thank you guys, and see you next time.